Alright, so welcome to part 3. Hopefully you're able to get this one figured out on your own. I'll reveal the answers in case you've tried already. Um, so again, once we did some simplification, collected all of our tan x terms together, it becomes just like all the other problems we solve. So tan x is 13 over 5. We check to see where tan x is positive, and hopefully you can see from the cast rule that that happens in two quadrants. So tan is positive in quadrant 3 and quadrant 1. Okay, so if I want to find alpha, that's going to be the tan inverse of 13 over 5. Which a quick calculation tells me it will be 68.96 to 2 decimal places. Okay, so again, look at your two quadrants. We've got quadrant 3 and quadrant 1. Okay, so in quadrant 1's nice and easy, right? Because our x value is going to be alpha, so we get 68.96 as a possible answer. Okay, quadrant 3 is a little bit trickier. We have to go x being equal to 180 degrees plus alpha, which will give us 248.96. Okay, so again, two answers. Okay, what I'd like you guys to do now, please try F on your own and see what you can get out of it. Okay, and again, just push play and you're ready to see the answer. Alright, so there are the answers, so you can check them out. One thing I will mention here, when you're solving, I know we're sort of hardwired to change every secant, cosecant, cotan we see to its reciprocal ratio, so we can work with the primary ratios instead. But don't do that right away, right? Don't complicate things by introducing reciprocals right now. Isolate for secant x first, so collect all your secant x terms, and once you have secant completely isolated as you do down here, when you get secant x equals negative 23 over 6, now convert to cosine x. So when you convert to cos x, you're taking the reciprocal of both sides, so secant x becomes cos x, negative 23 over 6 becomes negative 6 over 23. Yeah? So again, wait until you have secant isolated before you convert it to cosine. So if cosine is negative, that tells you we're looking at quadrants 2 and 3. So once we find alpha, we get 74.88. In quadrant 2, x is 180 minus alpha. In quadrant 3, x is 180 plus alpha. So we get our two answers there. Okay, so a lot going on there. Let's look at a few other types of problems here. So these next two I want you to figure out exactly. Okay, and they look a bit more complicated than some of the other ones you've seen so far. However, it's actually not too bad. So we have tan x times bracket tan x minus 1 equals 0. Just to get an idea of what's going on here, picture, I'm not saying we have to do this, but picture if a was equal to tan x, or whatever letter we want. I'm just going to pick a. And this would be the same thing as a times a minus 1 equals 0. And this would actually be a quadratic equation, which would have two solutions, one where a equals 0 and one where a minus 1 equals 0. Okay, so you could go through and you could solve each one of these for a. So a is 0 over here, and a is equal to 1. Okay, it's very similar, except instead of a, we have tan x. So if you don't want to do this substitution, that's fine. We can go straight from here and say, okay, we have two factors here. We have tan x, and we have tan x minus 1. It's equal to 0 on this side of the equation. So with any quadratic equation, you know, as you know from solving quadratics the last couple of years, you want everything factored on one side and 0 on the other, which is what we already have. Okay, I've given you that part already. So it means we have two solutions, two factors, two equations to solve here. One where tan x equals 0, and the other one where tan x minus 1 equals 0. Okay, and both these are equations we need to solve. Okay, so for tan x equals 0, we can go about trying to solve that. I'll deal with that one later, actually. Let me deal with this one first. The one in red here, I got tan x will be equal to 1. And I know we can use our calculator on this, but I want us to figure this out exactly, which means if it's exact, we should be able to figure out from one of two things, from the graph or from one of our special triangles. So our tan ratio of 1 should look familiar to us because it comes from our 45, 45, 90 triangle. Okay, so in that triangle we have side lengths of 1, 1, and root 2. So it's tan of 45 degrees equals 1. So right from here we can say that alpha is equal to 45 degrees. Okay, why is it alpha? Why is it not x? Remember, we're solving on 0 to 360, so if I have tan x being a positive value right here, so if tan x is positive, that happens in 2 quadrants. That would be quadrant 1 and quadrant 3. Okay, so using the fact that I know this comes from a special triangle, alpha would be the tan inverse of 1, okay, which I know to be 45 degrees. Okay. And now that I know that my answers are in quadrant 1 and quadrant 3, well, then I'm off to the races. So in quadrant 1, theta equals alpha. Sorry, not theta, x. Keep making that mistake. X equals alpha, so x is 45 degrees. Okay, and in quadrant 3, I'm going to have x being equal to 180 degrees plus alpha, which will give me 225. Okay, so I get these two answers from this factor. Now I've got to look at the answers I get for tan x equals 0. Now, tan x equals 0 is a little bit hard to figure out here. I mean, where is the tan ratio equal to 0? If you try to solve this on your calculator, you're going to get an x value of 0, which is all well and good, but where does that come from? This one might actually help if you know the graph of the parent function. So let's go take a look at the graph here. Okay, so here's tan x, and it's graphed from 0 to 360. So where is tan x equal to 0? Well, you can see on the graph it happens 3 times. Once, twice, and 3 times. So you have 3 possible solutions: 0, 180 degrees, and 360 degrees. So knowing the graph there will help us get our answers for that one. So having an idea what the parent functions for sine x, cos x, and tan x can be helpful, because this one gives you 3 solutions right here. This one gives you 2 solutions down here. So altogether, we actually have 5 solutions for this guy. Okay, 0, 180, 360, 45, and 225. Okay, so I'm just going to set up the second one for you, then let you solve it on your own. So just to make some space here. So here I actually have 3 factors. But again, the nice thing is it's all factored and it's all equal to 0. So I'm going to have 1, 2, 3 factors. Since the whole thing's factoring equal to 0, we get 3 different equations we need to solve. So the blue one here tells us that we're trying to solve sine x equals 0. Okay, the black one tells us we're trying to solve sine x plus 1 equals 0. Okay, and I'll put the red one over here, which tells us that 2 sine x plus 1 equals 0. Okay, so all these are 3 different equations we have to solve using the methods we've already been using for the past few examples. So let's do them one at a time. Let's deal with 2 sine x plus 1 equals 0. So 2 sine x plus 1 equals 0 is going to solve into 2 sine x equals negative 1. So sine x equals negative a half. Okay, so I'm going to let you try and solve for that one exactly. Sine x equals 0. Sine x is already solved. I'll let you try and solve that one. You might want to think about the graph for that one. And here we're going to get sine x equals negative 1. And again, I want you to try and solve for that one. So take a few minutes and think about it and see what you can come up with. And again, push play and you're ready to go through the answers. Okay, so you get a boatload of different answers for this one. Let's take it through step by step here. So I'm going to start with the red one, 2 sine x plus 1 equals 0, which led me to sine x equals negative a half. So sine x, the sine ratio is negative in 2 quadrants. It's going to be quadrant 3 and quadrant 4. So if I want to find the alpha, alpha will be the sine inverse of positive a half. Now, because I want this exactly, we should recognize that the sine ratio of 1/2 occurs in one of our special triangles, the 30, 60, 90 triangle. So when I do that, if I look inside this triangle, the sine ratio is 1/2, opposite over hypotenuse, when my angle is 30 degrees. So that will give me an alpha of 30 degrees. I can look in quadrant 3 and quadrant 4 then to find my 2 answers. In quadrant 3, x is 180 degrees plus alpha, and in quadrant 4, x is 360 degrees minus alpha. So I get 210 and 330. So that accounts for 2 of my answers. Okay, and we get a whole bunch more. So sine x equals 0. Okay, I want it exact. This doesn't come from one of our special triangles. It comes from the graph. So the graph of sine x is one of our parent functions. Let's take a look at the graph here. So here's sine x, and you can see sine x is 0 3 times. There, there, and there. So we get answers at 0, 180, and 360 degrees. So from the graph, we now get these 3 answers. Now looking at the case in black here where sine x equals -1, again, -1 is one of those, it's the smallest value on the sine function. So let's take a look at the graph and see where that happens. Okay, so where is sine x equal to -1? Well, sine x is equal to -1, and just clearing this extra stuff out of the way here. Sine x equals -1, looking on the graph, oh, right here, one spot. Okay, so at 270 degrees, we get yet another solution. So all told, we get 2 solutions from here, 3 from here, and 1 from here. So we actually wind up with 6 solutions overall. Okay, so that one's a little bit tricky. So if I'm asking you to solve it exactly, it means one of 2 things. It means the ratios the ratios that you're trying to solve will come from one of our special triangles, or it's ones that we can evaluate using the graph. Alright, just got a couple more examples to try. We're just going to try a few more complicated ones. Now, once we get into these, you'll see for the first time we actually see some quadratics involved. So here we have cos squared x and 16 cos x. So this is actually a quadratic equation. Now, I don't want us to panic here. We've solved quadratic equations before. I know not involving trig, but I mean, if you picture here that if we were to let a be equal to cos x, okay, with that small little substitution there, we could change this equation very quickly into 15a squared plus 16a minus 7 equals 0, which all of a sudden becomes a lot, at least friendlier to look at. Now, I know we can't ignore the fact that it was originally cos x, but this is something we can at least factor. Okay, now remember, going back to grade 10 and 3M if you took that course, any quadratic equation we want to solve, we're looking at everything over on one side, 0 on the other, and then we can either use factoring or quadratic formula. So factoring would be faster if you can get it to work, and this one actually does factor. So I'm going to take a minute and do that over here. So I'm going to do 15a squared, and then minus 7. Okay, so need 2 numbers that multiply -105, add to 16, that'll be 21 and -5. So that will give me here 5a and 3a, and this will be -1 and plus 7. So this factors into 5a plus 7, 3a minus 1. Okay, and again, once it's nicely factored, we can actually start solving for a. So this would mean that using this, if 5a plus 7 would be equal to 0, or a equals -7 over 5, or 3a minus 1 equals 0. Okay, so that one leads to there. 3a minus 1 equals 0, which means that a equals 1 over 3. Okay, and what this gives us is 2 different equations that we need to solve. So now, unfortunately, we can't ignore the fact that we originally had cos x in there, not a. So we make that substitution back in. So we'll say that now we have cos x equals -7 over 5. And cos x equals 1 over 3. And what I'm left with here is 2 completely different equations that I need to be able to solve. Okay, so I'll let you guys try and solve these ones on your own. Okay, and again, push play and you're ready to see how this one finishes up. Okay, let's quickly run through this one. So the first one here, cos x equals -7 over 5, that actually has no solution because you have cos x being smaller than -1, which cannot exist. So that one's not too bad, it gives you no answer. This one, cos x equals 1 over 3, cos is positive in quadrants 1 and 4. So we find our alpha being 70.53 degrees, and we use quadrants 1 and 4 to get our answers. So we're going to have to finish this one up in part 4, unfortunately, but one thing I just want to mention here, a lot of you like using quadratic formula for the complex trinomials. There's nothing wrong with that. You have to be a little bit careful here. So remember, when you're solving it, we'd actually replaced cosine x with another variable. So if you're using the quadratic formula, set the quadratic formula equal to cos x to get your solutions, not x. Okay, so we'll see you in part 4.